It was early morning on the 27th of August in the year 1939 at the Marionette airfield in northern Germany. A strange-looking aircraft sat on the runway waiting for its moment to change history forever. The small plane lacked a propeller, which was the standard feature of every flying machine known to mankind at that time. Instead, it had a gaping hole in its nose and a sleek fuselage that looked unfinished to the casual observer. The pilot Erich Warsitz climbed into the cramped cockpit with a mix of anxiety and determination. He knew that what he was about to attempt had never been done before in the history of aviation. The engineers standing by the tarmac held their breath as the engine whined to life. The stakes could not have been higher for the nations of Europe as the dark clouds of conflict gathered on the horizon. Traditional piston engines were reaching their physical limits and could not push aircraft much faster than 400 miles per hour without severe efficiency loss. The nation that could master a new form of propulsion would hold dominance over the skies in the coming war. Military leaders and aircraft designers knew that speed was life in aerial combat, but they were hitting a technological wall. The propeller blade tips were approaching the speed of sound, causing shock waves and drag that no amount of horsepower could easily overcome. A radical new solution was needed to break through this barrier. Enter Frank Whittle, who was a brilliant officer in the Royal Air Force of the United Kingdom. He was a man possessed by a singular vision that most of his superiors considered absolute madness. Whittle believed that a gas turbine could be used to produce a powerful jet of air to thrust a plane forward. He was not alone in this pursuit, though he did not know it at the time. Across the English Channel, a young German physicist named Hans von Ohain was working on a remarkably similar concept. These two men were the protagonists of a technological race that would define the 20th century. They worked in secrecy and often faced ridicule from the established experts of the aeronautical world. The burning question that haunted both inventors was whether their metal creations could withstand the immense heat and stress of operation. Critics argued that the materials required to build a functional jet engine simply did not exist. They claimed that the turbine blades would melt or shatter under the centrifugal forces and high temperatures needed for thrust. Could a machine truly suck in air, compress it, mix it with fuel, and blast it out the back without exploding? The skepticism was so deep that Frank Whittle allowed his original patent to lapse because he could not afford the renewal fee. The establishment believed the idea was scientifically sound on paper, but practically impossible to engineer. The reveal came with a roar that shook the ground beneath the wheels of the Heinkel He 178 on that August morning. As Erich Warsitz pushed the throttle forward, the aircraft surged ahead with a smooth and continuous power that felt unlike the vibration of a piston engine. The plane lifted off the runway and climbed rapidly into the sky-reaching speeds that promised a new era of flight. It was a successful flight that lasted only a few minutes, but it proved the concept was viable. Just a few days later, the German invasion of Poland began, and the world was plunged into World War II. The jet engine had arrived just as humanity entered its darkest conflict. Frank Whittle continued his work in the United Kingdom under the banner of a small company called Power Jets Limited. His resources were scarce, and his team worked in a derelict foundry that was freezing cold in the winter. Despite the lack of government interest initially, Whittle managed to get a prototype engine running on a test bench. The engine, known as the Woo, screamed with a terrifying noise that sent people running for cover. It was temperamental and dangerous, often accelerating out of control during tests. Whittle himself often stood next to the screaming turbine, ready to shut off the fuel supply if disaster struck. His bravery and persistence kept the British jet program alive during those lean years. While Whittle struggled for funding, Hans von Ohain enjoyed the support of the aircraft manufacturer Ernst Heinkel. Heinkel was an ambitious man who wanted his company to be at the forefront of aviation technology. He provided von Ohain with the resources and staff needed to develop the He S-3 engine, which powered the first flight. However, the German Air Ministry was slow to recognize the potential of this new invention. They were focused on producing thousands of conventional fighters for the immediate war effort rather than investing in unproven technology. This delay gave the Allies a crucial window of opportunity to catch up in the race for jet supremacy. The British government finally realized the importance of the work Frank Whittle was doing as the war intensified. The Gloster Aircraft Company was contracted to build an airframe that could accommodate the new engine designed by Whittle. The result was the Gloster E-2839, which was a small and experimental aircraft designed solely to test the engine. It took to the skies in May of 1941, almost 2 years after the German success. The pilot Jerry Sayer flew the aircraft for 17 minutes and reported that it was a delight to fly. The British finally had a jet aircraft, and the race was now truly on. Across the Atlantic Ocean, the United States was alerted to the British success and requested access to the technology. General Henry Arnold of the United States Army Air Forces arranged for a Whittle engine and a set of drawings to be flown to America in secret. The General Electric Company was tasked with copying and improving the design, while Bell Aircraft began work on a fighter jet. The result was the Bell P-59 Aerocomet, which became the first American jet fighter. Although it was not particularly fast and never saw combat, it gave American engineers vital experience. This technology transfer laid the foundation for the future aerospace dominance of the United States. In Germany, the development of jet aircraft shifted from the experimental Heinkel to the more established Messerschmitt Company. The engineers that were working on a design that would become the legendary Me 262. This aircraft was far more advanced than anything the Allies had on the drawing board. It featured swept wings and 2 axial flow jet engines mounted under the wings. The axial flow design was more aerodynamic than the centrifugal design used by Whittle, but it was also more complex and prone to failure. The German engineers faced constant shortages of heat-resistant alloys like nickel and chromium due to the Allied blockade. The development of the Me 262 was plagued by political interference from the highest levels of the Nazi leadership. Adolf Hitler demanded that the aircraft be used as a high-speed bomber rather than an interceptor. This decision required design changes that delayed the deployment of the aircraft by several critical months. The engineers and pilots knew that the Me 262 was a superior fighter that could decimate the Allied bomber formations. However, they were forced to modify the airframe to carry heavy bombs, which ruined its performance. This strategic blunder is often cited as a turning point that prevented the Luftwaffe from regaining air superiority. Meanwhile, in the United Kingdom, the Gloster Meteor was being prepared for active service. It was a twin-engine design that was more conservative than the German jet, but also more reliable. The Meteor entered service in July of 1944, becoming the first Allied jet fighter to see combat. Its first mission was not to fight other aircraft, but to intercept the V-1 flying bombs that were terrorizing London. The speed of the Meteor allowed it to catch the pulse jet-powered missiles and tip them over with its wingtip. This was a dangerous maneuver that required immense skill from the pilots. The German Me 262 finally entered service as a fighter in late 1944. When it appeared in the skies over Europe, the Allied pilots were stunned by its speed. It could fly nearly 100 miles per hour faster than the best piston engine fighters like the P-51 Mustang. The American bomber crews called it the Swallow because of its swept wings and rapid attacks. The Me 262 would dive through the bomber formations, firing its 4 30mm cannons with devastating effect. The only way the Allies could counter it was to attack the jets when they were taking off or landing. The psychological impact of the jet engine on the combatants of World War II cannot be overstated. For the pilots in conventional aircraft, seeing a plane without a propeller moving at such incredible speeds was terrifying. It signaled that the era of the piston engine was coming to an abrupt end. The sound of the jets was a high-pitched scream that was distinct from the rumble of traditional aircraft. Although the German jets arrived too late and in too few numbers to change the outcome of the war, they proved that the future of aviation belonged to the turbine. The technology had graduated from a theoretical possibility to a lethal reality. Another German innovation that appeared late in the war was the Arado R-234 Blitz. This was the first operational jet-powered bomber in the world. It was a sleek high-wing monoplane that used the same Jumo 4 engines as the Me-262. The Arado was so fast that it was almost impossible for Allied fighters to intercept it. It was used primarily for reconnaissance missions over the United Kingdom and the front lines. The existence of such an aircraft demonstrated that jet propulsion was suitable for more than just interceptors. It pointed the way toward the future of commercial and military transport. As the Allied armies advanced into Germany, they raced to capture the advanced technology and the scientists who created it. This effort was known as Operation Paperclip in the United States. Teams of intelligence officers and engineers scoured the German research facilities for documents and hardware. They found prototypes of swept-wing fighters and advanced engine designs that were years ahead of Allied research. Hans von Ohain and many other German scientists were brought to the United States to continue their work. This influx of knowledge accelerated the American jet program significantly during the early years of the Cold War. The immediate post-war period saw a rapid evolution of jet technology as nations applied the lessons learned during the conflict. The British and Americans moved quickly to adopt the swept-wing data captured from the Germans. The straight wings used on the Gloster Meteor and the P-80 Shooting Star were found to be inefficient at high speeds. The swept wing delayed the onset of shock waves and allowed aircraft to fly closer to the speed of sound. This aerodynamic breakthrough, combined with more powerful engines, set the stage for the next major milestone in aviation history. The sound barrier was the next target. On the 14th of October 1947, a bright orange bullet-shaped aircraft dropped from the belly of a B-29 bomber. The pilot was Chuck Yeager, a fearless captain in the United States Air Force. The aircraft was the Bell X-1, which was powered by a rocket engine rather than a jet, but the principles of high-speed flight were the same. Yeager pushed the aircraft past Mach 1, breaking the sound barrier for the first time in level flight. The sonic boom that echoed across the Mojave Desert announced that the compressibility problems that had plagued early jets could be overcome. This achievement opened the door for supersonic jet fighters. The Korean War became the first conflict where jet fighters fought against other jet fighters in large numbers. The skies over MiG Alley saw the Soviet-built MiG-15 clash with the American F-86 Sabre. Both aircraft featured swept wings and were powered by advanced jet engines. The dogfights were fought at speeds and altitudes that were unimaginable just a decade earlier. The pilots had to grapple with high G-forces and the split-second reaction times required at 600 miles per hour. This conflict solidified the jet engine as the standard propulsion system for all future combat aircraft. While the military was pushing the boundaries of speed, the commercial sector was looking at how jets could revolutionize travel. The British aviation industry took the lead with the development of the de Havilland Comet. It was a beautiful aircraft with engines buried in the wing roots and large rectangular windows. When it entered service in 1952, it cut travel times in half and offered a smooth, vibration-free ride. Passengers were amazed by the quiet luxury of flying in the stratosphere above the weather. The Comet was the pride of Britain and seemed to herald a new golden age of travel. Tragedy struck the Comet program when several aircraft disintegrated in mid-air, killing everyone on board. The fleet was grounded and a massive investigation was launched to find the cause. Scientists discovered that the square windows created stress concentrations in the metal fuselage. The constant pressurization and depressurization cycles caused metal fatigue, which led to catastrophic failure. This was a painful lesson for the aviation industry, but it led to stricter safety standards and better understanding of materials. The windows on all future jetliners would be oval or round to distribute the stress evenly. The United States aviation industry watched the Comet disaster and learned from the British mistakes. The Boeing company took a massive gamble by developing the Dash 80 prototype, which would become the Boeing 707. The company president Bill Allen bet the entire net worth of the company on this project. In a famous demonstration, pilot Tex Johnston performed a barrel roll with the Dash 80 over Lake Washington to impress potential buyers. The Boeing 707 entered service and quickly became the dominant airliner of the 1960s. It ushered in the jet age for the general public, making international travel accessible to the masses. The world began to shrink as jetliners connected continents in a matter of hours rather than days. A journey from London to New York, which used to take days on a ship or over 12 hours on a piston plane, now took less than 7. Business people could attend meetings on different continents in the same week. Tourism exploded as exotic destinations became reachable for middle-class families. The jet engine did more to globalize the economy and culture than any other single invention of the 20th century. Airports expanded into massive hubs of commerce and activity. In the military realm, the 1950s saw the development of the Century series fighters in the United States. These were the first supersonic fighters designed to carry nuclear weapons and intercept Soviet bombers. Aircraft like the F-104 Starfighter were built like missiles with tiny wings and immense engines. They sacrificed maneuverability for raw speed and climb rate. The Cold War arms race drove engine manufacturers to create turbines with afterburners that dumped raw fuel into the exhaust for extra thrust. The noise of these jets became the soundtrack of air bases around the world. The quest for speed culminated in the development of the Lockheed SR-71 Blackbird. This reconnaissance aircraft was designed to fly at 3 times the speed of sound and at altitudes above 80,000 feet. Its engines were a marvel of engineering that acted as ramjets at high speeds. The Blackbird was so fast that the standard evasion maneuver for a surface-to-air missile was simply to accelerate. The friction of the air heated the titanium skin of the aircraft to over 500 degrees. It remains the fastest air-breathing manned aircraft ever built. As the 1960s progressed, the focus of commercial aviation shifted from pure speed to efficiency and capacity. The low-bypass turbojet engines used on early airliners were noisy and thirsty for fuel. Engineers developed the high-bypass turbofan engine, which moved a massive amount of air around the core of the engine. This design was much quieter and far more fuel-efficient. The increased thrust allowed for the creation of wide-body jets that could carry hundreds of passengers. The era of the jumbo jet was about to begin. The Boeing 747 was the first of these wide-body giants, and it changed the economics of air travel forever. It featured a distinctive hump and a double-deck layout that made it instantly recognizable. The 747 could carry over 400 passengers, which significantly lowered the cost of a ticket. It democratized air travel, allowing millions of people to fly for the first time. The high-bypass engines made it possible to lift such a heavy machine while burning less fuel per passenger than smaller jets. The 747 became an icon of the skies and reigned as the queen of the air for decades. While subsonic travel became cheaper, a joint British and French team pursued the dream of supersonic commercial transport. The result was the Concorde, a stunning delta-winged aircraft that could fly at twice the speed of sound. It catered to the wealthy elite who were willing to pay a premium to cross the Atlantic in 3 hours. The Concorde was a technological masterpiece, but an economic failure. The sonic booms it created meant it was banned from flying supersonically over land, which limited its routes. It remained a niche service until its retirement in the early 21st century. The Soviet Union also built a supersonic transport known as the Tupolev Tu-144. It looked remarkably similar to the Concorde, leading to allegations of industrial espionage. The Tu-144 was faster and larger than its Western counterpart, but it was crude and unreliable. It suffered a terrible crash at the Paris Air Show in 1973, which tarnished its reputation. The aircraft saw very limited service carrying mail and cargo before being retired from passenger flights. It served as a reminder that being first or fastest does not always guarantee success in the aviation industry. The energy crises of the 1970s forced engine manufacturers to focus even more intensely on fuel efficiency. The price of jet fuel skyrocketed, making older engines too expensive to operate. This drove the development of advanced materials like carbon fiber composites for fan blades. The engines became larger and the bypass ratios increased significantly. Computer-aided design allowed engineers to optimize the airflow through the compressor and turbine stages. These advancements kept the airline industry profitable despite the volatile oil market. Modern jet engines are marvels of computer control and material science. They operate at temperatures that are higher than the melting point of the metal alloys they are made of. This is possible due to intricate cooling channels and ceramic thermal barrier coatings. The Full Authority Digital Engine Control, or FADEC systems, monitor every parameter of the engine thousands of times per second. They adjust the fuel flow and variable stator vanes to ensure peak performance and safety. The reliability of these engines is so high that twin-engine aircraft are now allowed to fly long distances over open oceans. The legacy of Frank Whittle and Hans von Ohain is visible in every airport and airbase around the world. Their independent genius ignited a revolution that reshaped the geopolitical and economic landscape. From the terrifying scream of the first experimental jets to the quiet hum of a modern turbofan, the journey has been one of constant innovation. The jet engine conquered the distance between nations and made the world a smaller and more connected place. It stands as one of the greatest engineering achievements in human history. As we look to the future, the development of jet propulsion continues to evolve. Engineers are exploring open rotor designs and hybrid electric propulsion to further reduce emissions and noise. The dream of hypersonic travel, which would allow flights from New York to London in 1 hour, is being pursued by military and civilian researchers. The spirit of innovation that drove the pioneers of the 1930s is still alive today. The quest to fly higher, faster, and more efficiently will never truly end as long as humanity looks to the sky. The story of the jet engine is a testament to the power of human ingenuity in the face of impossible odds. It reminds us that the barriers we face are often just technical challenges waiting for a brilliant mind to solve them. From the humble beginnings in a British foundry and a German garage to the edge of space, the jet engine has propelled us forward. It has changed the way we fight wars, the way we do business, and the way we understand our planet. The whisper of time carries the roar of the jet engine as a permanent echo of our progress.